Hello and welcome back. In this video we're going to take a look at the cross product, also referred to as the vector product. Now the cross product's very useful, although it's looked at as sort of the more difficult of the two kinds of multiplication to perform with vectors. The first thing that makes it a little bit more tricky is you're not getting a scalar value. You're actually getting a new vector out of this. So when you multiply, or that is when you cross multiply two vectors together, you get a new vector. Now this vector has two properties that are very important to us. The first thing is that it's normal or perpendicular, that is at 90 degrees to the two vectors you're crossing together. This is great. We use this all the time for a lot of different applications. The easiest one to talk about is, of course, calculating the normal of a surface. That is, what direction that surface faces. And this is used extensively in light calculations. Now, the normal can also be used to determine offsets. So the idea is that maybe you have a vector that faces forward, a direction vector, but you want to figure out how far to the left or to the right. Maybe you're trying to draw a lane or a road surface. Well, we can take the cross product of that forward vector with an up vector, and that will return to us a vector that's 90 degrees to those two, which is our right or left vector, depending upon our order. Once we have that information, we can now step to the left and step to the right in our coordinate system very easily. You might have noticed I said to the left or to the right, and that is completely dependent on the order of the vectors you're multiplying. So in this case, what we've got here, just for notation up here, is our two vectors. Our green vector has the components ax, by, and cz, where a, b, and c are the constants, and x, y, and z are, of course, the axes we're moving in, or if you want to think of them as I, j, and k, and those are our basis vectors, you can do that as well. And of course, the second vector in red is our dx, ey, and fz. Here's the full equation for how the cross product works. You'll notice we have this magnitude times the magnitude of the other vector. If you're dealing with unit vectors, you can ignore these terms, as the magnitudes will be equal to 1, vastly simplifying things. Once again, this is why we make sure we work with unit vectors a lot of the time, because these operations become far easier. In this case, we're dealing with the sine of the angle between these two values. Now, this is the equation that we deal with when we have two vectors for calculating the vector product. Now, you'll notice we have our I, j, and our k components. So to form the I component, or our x component, what do? Well, we take the y component and multiply it by the z component, and subtract from that the z component multiplied by the y component of the second vector. Notice how the x's have zero influence in this case. Same thing for the j, or the yth component. We actually omit the y information and only use the z and the x, and of course, following suit, for the z, we cross that out and we're only using the x and the y information. And once we've done that, we get some interesting things. So first we get a new vector, and the magnitude of that vector is going to be the area of the parallelogram formed by these vectors. That is, if you were to take these vectors and put them on each other's heads, you would then create this parallelogram you see right here. Okay, so here's a deeper explanation of what's going on, what we're trying to solve for. Once again, here's our equation at the top. And what we're basically doing when you think of the cross product is we're trying to calculate this new perpendicular vector. And I'm going to call this vector v, and we have question marks, question mark 1, 2, and 3. These are our constants. That is, how much in the x direction are we, how much in the y, and how much in the z. Solve for the x component, solve for the y, and solve for the z. So I've taken those components here and split them out so we can see each operation. So for the x, what we do is we ignore the x information. So I've drawn a line through it. The outcome here is going to be x. Now we only fixate on the remaining two components. That is the y's and the z's. The y component of the first vector times the z component in the second vector, subtract the z component in the first vector times the y component of the second vector. Now when we take a look at y, once again I'm going to draw a line through the y area. I'm not using that. Now this is where you might end up finding a different equation for the cross or vector product. And there's a negative sign put into the other form of this equation. It's actually right here. Instead of a plus, instead of plus the jth component, it's a subtraction. This has to do with how individuals decide to remember this. For some reason in my brain, I like this form that we see here. The reasoning behind this is, if we draw a line right down the center, what happens here? Well, we've got this term, our z information that we start with, and then we wrap back around to the x's on the other side. For some people, that concept of wrapping back around to the other side is confusing. They see the x terms next to the z terms, and they start with the leftmost quantity. That is the x's and the z's. So they multiply the x and the z, and then of course the z and then the x subtracting. Now, if you think about this, if we did the opposite, that is, if we started with cz and multiplied that by dx and then subtracted ax from fz, what's happening here? Well, the negative term is either on the first part or the second part of this operation, right? That subtraction is either the first portion of the product or the second portion. So we can either make sure we wrap back around from the z to the x, or we can add a new negative value and just look at it as the x term minus the z term and so forth and so on. So that's where you get the difference of notation. And here you can see my nice little arrow. This is how I remember it. I wrap back around to the other side of the matrix as if it exists forever, basically, just keeps repeating. Now for the z, we of course cross out the z, we wrap back around, and now we do ax times ey minus by times dx. And that's how you get the result. So let's take a minute now and actually jump into a worked example. Mainly with that example, I'm going to want to show off how when we multiply a vector, the order really matters. That is, the cross product order matters. Dot product, it never matters because you just get that single scalar value back. But with the cross product, your vector will either face in a positive direction or a negative direction.